In this lecture, we'll find out the area of the green semicircle using two different methods. In the drawing, we have two semicircles. This is the white semicircle, this is the green semicircle. In addition, we know that line segment AC equals to 5 units in its length, line segment CB equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. So we start with the first method, and we join points P and B together by a straight line. And I will copy the white semicircle in a new page, and we will implement rule 7 in this white semicircle. Actually, this is the white semicircle that I go with on the original drawing. Here, AB is the diameter of this white semicircle, so I'll write it down. AB is the diameter of this white semicircle. By joining points P and B together by a straight line, we create the peripheral angle APB. This is peripheral angle APB, and this peripheral angle APB is subtended on AB. That is the diameter of this white semicircle, and therefore we can implement here rule 7. I'll repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing we have a circle, and we have this is line segment AB, that is the diameter of this circle, and we have here peripheral angle ACB, that is subtended on AB, that is the diameter of this circle, and therefore peripheral angle ACB equals to 90 degrees in its size. So whenever we have a peripheral angle that is subtended on the diameter of the circle, it must be equal to 90 degrees in its size. So we can actually implement rule 7 in our drawing. In our drawing, we have peripheral angle APB that is subtended on AB, that is the diameter of this white semicircle, and therefore peripheral angle APB must be equal to 90 degrees in size according to rule 7. So this peripheral angle APB equals to 90 degrees in size. In the next step, we'll join points P and C together by a straight line. And I'll copy the green semicircle in a new page, and we'll implement rule 7 on this green semicircle. Actually, this is the green semicircle that I copied from the original drawing. Here, side AP is the diameter of this green semicircle, so I write it down. By joining points P and C together by a straight line, we get here peripheral angle ACP. This is peripheral angle ACP that is subtended on AP, that is the diameter of this green semicircle. Therefore, peripheral angle ACP must be equal to 90 degrees in size according to rule 7. So this peripheral angle ACP is a right angle. Here, this is peripheral angle ACP, that is a right angle. And here, in this original drawing, angle A is a common angle that belongs to both triangles. Angle A, this angle A, belongs to the green triangle APC, and it also belongs to triangle APB. So angle A is a common angle that belongs to both triangles. So we define the size of this common angle A as alpha. So here, this is the common angle A, that is equals to alpha according to our definition. So in this white triangle APB, this angle equals to alpha, this angle equals to 90 degrees, therefore the missing third angle here must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this main right triangle ABC, this is the common angle, angle A, that is equals to alpha according to our definition. So this common angle A equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha in its size. In the next step, we prove that the right main triangle APC is similar to this right triangle APB according to angle similarity rule. So I'll copy those two right triangles in a new page and we prove that they are similar to each other according to angle similarity rule. So actually, those are the two right triangles that are going from the original drawing. In the next step, we'll prove that those two right triangles are similar to each other. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually, this is angle APB in the right triangle APB. And it is equals to this angle, that is actually angle ACP in the main triangle APC. Let's it again. angle APB in the right triangle equals to angle ACP in the green triangle. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha. That is a common angle that belongs to both triangles. Here we have angle alpha also here in the right triangle. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to angle alpha, as it belongs to this right triangle, it will be defined as angle PAB. And it equals to itself. So if we relate to angle alpha as it belongs to this green triangle, it will be defined as angle PAC. Because again, this equation means that angle alpha equals to itself. We just call to angle alpha two different names. So angle alpha equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So hopefully, this is angle ABP in the right triangle. And it is equal to this angle, that's actually angle APC in the green triangle. Repeat again, angle APB in the right triangle equals to angle APC in the green triangle. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the triangles in this right triangle APB are correspondingly equal to all the triangles in this right green triangle APC. Therefore, those two right triangles can go into each other. Those two right triangles are similar to each other according to angle similarity rule. So I'll write it down. We actually found out that the right triangle APB is similar, this is the sign of similar, to the green triangle APC. According to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB in the right triangle over side AP in the green triangle equals to side AP in the white triangle over side AC in the green triangle. Repeat again. We will derive that side AB in the white triangle or side AP in the green triangle equals to side AP in the white triangle or side AC in the green triangle. What is the length of side AB? From the drawing, it is very easy to see that side AB equals to AC plus CB. So side AB equals to AC, that is 5, plus CB, that is 1. So in total, AB equals to 5 plus 1, that is 6. And what is the length of side AC? Side AC equals to 5 units in its length, according to what is given as the question. So actually found out that AB is 6, AC is 5, so in total AB over AP equals to AP over AC. We get that this equation equals to 6 over AP equals to AP over 5. Okay, here of course multiply this equation and we get that 5 times 6 equals to AP times AP, that is AP square. 5 times 6 is 30, so 30 equals to AP square, or AP square equals to 30. We take a root out of this equation and we get that the missing side AP is equals to the square root of 30 units in its length. So actually this is the missing side AP and it is equals to square root of 30 units in its length. So write it down. AP is the diameter of this green semicircle, therefore AP over 2 is the radius of the green semicircle. So the radius R of this green semicircle equals to the diameter AP over 2. AP is square root of 30 and square root of 30 over 2 is the radius of this green semicircle. So the radius R equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of the green semicircle equals to the area of the circle, that is pi r square over 2. So write it down. The area of this green semicircle equals to pi r square over 2. And we just right now found out that the radius R of the green semicircle equals to the square root of 30 over 2. So in total, the area of the green semicircle must be equal to pi. R is equal to 30 over 2, therefore R square is equal to 30 over 2 square divided by 2. So the area of the green semicircle equals to pi. Square root of 30 square is 30. Over 2 square is 4 divided by 2. So the area of the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So here we have 30 over 2 is 15. So in total, the value of this expression equals to 15 pi over 4. 15 over 4 is 3.75. So in total, this expression equals to 3.75 pi and 3.75 pi equals to 11.78. So actually found out that the area of the green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equals to 11.78 square units. Repeat again. We actually found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, the area of this green semicircle equals to 11.78 square units. We finish with the first method. In the next step, I will present to you how to find out the area of this green semicircle according to the second method. In the second method, we'll join points P and B together by a straight line. And I will copy this white semicircle in a new page, and we will implement rule 7 on this white semicircle exactly as we did in the first method. Actually, this is the white semicircle that I go into the original drawing. AB is of course the diameter of this white semicircle, so I write it down. By joining points B and B together by a straight line, we can determine peripherical APB. This peripherical APB is subtended on AB, that is the diameter of this white semicircle. Therefore, according to rule 7, peripherical APB must be equal to 90 degrees in its size. This peripherical APB is a right angle according to rule 7. But it is subtended on AB, that is the diameter of this white semicircle. So here, peripherical APB equals to 90 degrees in size. So this is peripherical angle APB. This is a right angle according to rule 7. Actually, line segment AP is perpendicular to line segment PB, because this angle is a right angle, or line segment BP is perpendicular to line segment PA. PA is the diameter of the green semicircle, and we know that the center of any circle is always located on the diameter of the circle. So the center of this green semicircle must be somewhere between points A and P. So here this will be the center of this green semicircle. We define the center of this green semicircle as O. Point O is the center of this green semicircle. Point P is the point on the green semicircle itself. Therefore, PO is the radius of this green semicircle. So we define the radius of this semicircle as R. Therefore, PO equals to R according to our definition. Line segment BP is perpendicular to line segment PO. Therefore, line segment BP must be also perpendicular to PO. Why? Because if you have a straight line that is perpendicular to another straight line, then the straight line must be also perpendicular to the part of the straight line. Therefore, line segment BP must be also perpendicular to PO, or line segment BP must be also perpendicular to the radius PO of this green semicircle. And whenever you have a line segment that is perpendicular to a radius of a circle, you can implement rule 1. Actually, line segment BP is perpendicular to the radius PO at the end point, that is point P. Okay, so now we can implement rule 1 in this drawing because of the fact we have line segment BP that is perpendicular to the radius PO of this green semicircle. I repeat quickly on rule 1. According to rule 1, a tangent to a circle, tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and OM is the radius R of this circle, and according to this rule 1, line segment AB is perpendicular to the radius MO of this circle. So whenever you have a line segment that is perpendicular to the radius of a circle, then that line segment will be defined as a radius. That line segment is defined as a tangent. Line segment AB is a tangent to this circle at point M. Okay? Again, whenever you have a radius, whenever you have a line segment that is perpendicular to a radius of a circle, then that line segment is defined as a tangent according to rule 1. So now we can implement rule 1 in our drawing. Why? Because in our drawing we have line segment BP that is perpendicular to the radius PO of this green semicircle, and therefore according to rule 1, line segment BP is defined as a tangent to this green semicircle. Why? Because it is perpendicular to the radius PO of this green semicircle. So I write it down. Actually, I found out that line segment BP is a tangent to this green semicircle according to rule 1. So from this common external point B, we have tangent BP to this green semicircle. Actually, tangent BP is tangent to this green semicircle at point P. In addition, from the same common external point B, if we draw a straight line towards this green circle, it will cut the green circle, the green semicircle at 2 points, C and A. So from the same common external point B, we have also chord CA. Again, from this common external point B, we have tangent BP, and we also have chord CA. Therefore, we can implement here rule 10. I'll click quickly on rule 10. Rule 10 is true in any circle, so in any circle, if AB is any chord in the circle, we have here AB is the chord of the circle, and we have also PT is a tangent to this circle at point T. So in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. We can definitely implement rule 10 in our drawing. Why? Because in our drawing, if we focus on this common standpoint point B, from this common standpoint point B, we have tangent BP to this green semicircle, and we have also here chord CA. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, BP square equals to BC times BA. Again, BP square equals to BC times BA. BP square equals to BC times BA. So I write it down. Repeat again, if we focus on this common standpoint point B, according to rule 10, we get that BP square equals to BC times BA. BP is the missing tangent, so we leave it as it is. BP square equals to BC, BC is 1, times BA. BA in total equals to 1 plus 5, that is 6. So we found out that according to rule 10, BP square equals to 1 times 6, that is 6. BP square equals to 6. We take a root out of this equation, and finally we get that the missing tangent BP is equals to the square root of 6 units in its length. Finally, this is the missing tangent BP is equals to the square root of 6 units in its length. In the next step, I'll copy the right triangle APB in a new page, and we'll implement the Pythagoras theorem on this right triangle, triangle APB. AP is the missing side, this right triangle APB. Here by PT is a version for Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Side PB equals to the square root of 6 units in its length, and side AB equals to 5 plus 1, that is 6. So actually, this is the right triangle APB that are going to the original domain. According to the Pythagoras theorem, in this right triangle APB, AB squared, that is the square of the hypotenuse, equals to AP squared plus PB squared. Again, AB squared equals to AP squared plus PB squared. So I write it down. AB squared equals to AP square plus PB square. AB is 6, therefore AB square is 6 squared, that is 36. And it is equals to AP square. AP is the missing side, so we leave it as it is. Plus PB square. PB is square root of 6, therefore PB square is square root of 6 squared, it is 6. So in conclusion, we shall find out that 36 equals to AP square plus 6. We subtract 6 from this equation. And finally we get that the missing side AP square equals to 36 minus 6 is 30. We take a root out of this equation, and finally we get that the missing side AP equals to the square root of 30 units in its length. Okay, so this is the missing side AP, and is equals to the square root of 30 units in its length. AP is the diameter of this green semicircle. And it is equal to the square root of 30 units. If the diameter AP equals to the square root of 30, it means that the radius must be equal to half of it. So the radius R of this green semicircle equals to the diameter AP over 2. The diameter AP is square root of 30, and square root of 30 over 2 is the radius of this green semicircle. So R equals to the square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of this green semicircle equals to pi r square over 2. So it is pi r is equal to 30 over 2, therefore r square is equal to 30 over 2 square divided by 2. So the area of the green semicircle equals to pi, square root of 30 square is 30, over 2 square is 4 divided by 2. So it is pi, and 30 over 4 over 2 is 30 over 4 times 2. 30 over 2 is 15, so in total the value of this expression is 15 pi over 4. 15 over 4 is 3.75, therefore in total this expression equals to 3.75 pi, and 3.75 pi is 11.78. So actually found out that the area of the green semicircle according to the same method, according to the second method, is equals to either 3.75 pi square units, or in terms of numbers it is equals to 11.78 square units. This is exactly the same result that we got in the first method. Okay, again, actually in both methods we found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers it is equals to 11.78 square units. So in the next step I will summarize the lecture. We start with the first method. So in this lecture, we found out the area of this green semicircle using two different methods. Okay, so in the drawing we have two semicircles. Line segment AC equals to 5 units in its length, line segment BC equals to 1 unit in its length. Again, our mission is to find out the area of this green semicircle. So in the first method, we join points P and B together by side line, and then I copied this white semicircle in the new page, and we implemented all 7 in this white semicircle. Actually, this is the white semicircle that according to the original drawing. AB is of course the diameter of this semicircle. By joining points P and B together by side line, we created a peripheral angle APB. Peripheral angle APB is subtended on AB, that is the diameter of this white semicircle, and therefore, according to Rule 7, any peripheral angle that is subtended on the diameter of the circle must be equal to 90 degrees inside. Therefore, peripheral angle APB is a right angle. Okay, so in the next step, I actually joined points P and C together by side line, and I copied this green semicircle in a new page and implemented Rule 7 on this green semicircle. Actually, this is the green semicircle that according to the original drawing. AP is of course the diameter of this green semicircle. By joining points P and C together by side line, you get the peripheral angle ACP. This peripheral angle ACP is subtended on AP, that is the diameter of this green semicircle. Therefore, according to Rule 7, peripheral angle ACP must be equal to 90 degrees in size. It is very easy to see from this original drawing of the question that this angle A is a common angle that belongs to both triangles. Angle A belongs to the green triangle APC, and this angle A also belongs to triangle APB. Therefore, angle A is a common angle that belongs to both triangles. So we define the common angle A, the size of this common angle A is alpha. So this is the common angle A that is equals to alpha according to our definition. So in this right triangle APB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this green triangle APC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. In the next step, we proved that this green right triangle APC is similar to this white triangle APB according to angle similarity rule. So I copied those two right triangles in the new page, and we prove that those two right triangles are similar to each other. So actually, those are the two right triangles that according to the original drawing. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle, it belongs to both triangles. We have angle alpha also near the green triangle. So we can find out that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I actually proved that all the three angles in this right triangle APB are correspondingly equal to all the three angles of this green triangle APC. Therefore, those two right angles are similar to each other according to angle similarity rule. So if I return again, the right triangle APB is similar, this is the side of similar, to the green triangle APC according to angle, similar rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AB in this right triangle over side AP in this green triangle equals to side AP in this white triangle over side AC in this green triangle. And repeat again. We derive that side AB in the white triangle over side AP in the green triangle equals to side AP in the white triangle over side AC in the green triangle. AB is 6, AC is 5. Therefore, this equation in total equals to 6 over AP equals to AP over 5. We just substitute AB by 6 and AC by 5 and found out that 6 over AP equals to AP over 5. Because multiplying this equation, we found out that 5 times 6 is 30. So 30 equals to AP times AP, that is AP squared. We took a root out of this equation and finally found out that the missing side AP equals to the square root of 30 units instead. So actually, this is the missing side AP, that equals to the square root of 30 units inside. AP is the diameter of this green semicircle. So the diameter AP equals to the square root of 30, and therefore the radius must be equal, the radius R of this green semicircle must be equal to half of it. Again, the radius R of this green semicircle must be equal to the diameter AP over 2. The diameter AP is square root of 30, therefore square root of 30 over 2 is the radius of this green semicircle. The radius R equals to square root of 30 over 2. Our mission is to find out the area of this green semicircle. The area of this green semicircle equals to the area of the circle over 2. The area of the circle is pi r squared, so pi r squared over 2 is the area of this green semicircle. I repeat again. The area of this green semicircle equals to pi r squared over 2. So it is pi, r is square root of 30 over 2, therefore r squared is square root of 30 over 2 squared divided by 2. So the area of the green semicircle equals to pi, and square root of 30 squared is 30, over 2 squared is 4 divided by 2. So the area of the green semicircle in total equals to pi times 3 over 4 over 2 times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So in total, the value of this expression is 30 pi over 4 times 2. Here 30 over 2 is 15. So in total, the value of this expression is 15 pi over 4. 15 over 4 is 3.75. Therefore, in total, the value of this expression is 3.75 pi. And 3.75 pi is equals to 11.78. So in conclusion, we found out that the area of this green semicircle equals to either 3.75 pi square units, so in terms of numbers, it is equal to 11.78 square units. We finish with the first method. In the next step, I presented to you how to find out the area of this green semicircle according to the second method. In the second method, we join points P and B together by a straight line. Then I copied this white semicircle in a new page and we implemented rule 7 on this white semicircle. This is the white semicircle that I copied from the original drawing. AB is of course the diameter of this semicircle. By joining points P and B, we created a peripheral angle APB. Peripheral angle APB is subtended on AB, that is the diameter of this semicircle, and therefore according to rule 7, peripheral angle APB must be equal to 90 degrees in its size. Okay, so actually, this is peripheral angle APB, that is a right angle. So peripheral angle APB equals to 90 degrees. That is to say, line segment BP is perpendicular to line segment PA. Again, line segment BP is perpendicular to line segment PA. PA is the diameter of this green semicircle, and we know that the center of any circle or semicircle must be located on the diameter of the circle of the semicircle. Therefore, the center of this green semicircle must be located between point P and A, because PA is the diameter of this semicircle. So this is point O, that is the center of this green semicircle. We know that BP is perpendicular to the diameter PO, therefore BP must be also perpendicular to the radius PO. Okay, because if a line segment is perpendicular to another line segment, then that line segment must be also perpendicular to a part of the line segment. Therefore, line segment BP must be also perpendicular to the part of PA, that is PO. PO is the radius of this green semicircle. So in conclusion, we can find out that line segment BP is perpendicular to the radius R of this green semicircle, and therefore we can implement here rule 1. And please quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So we have here a circle, and line segment OM is the radius R of this circle, and according to rule 1, line segment AB is perpendicular to the radius MO. Again, line segment AB is perpendicular to the radius MO, and because of the fact that line segment AB is perpendicular to the radius MO, line segment AB is defined as a tangent to this circle. Actually, line segment AB is tangent to this circle is point M. So from rule 1, we can conclude that whenever we have a line segment that is perpendicular to a radius of a circle, then that line segment is defined as a tangent to the circle. We can implement rule 1 in our drawing. Why? Because in our drawing we have line segment BP that is perpendicular to the radius PO of this green semicircle, and therefore according to rule 1, line segment BP must be tangent to this semicircle. So line segment PB is a tangent to this semicircle at point P. In addition, so from the common extent point B, we have tangent BP to this green semicircle, and from the same common extent point B, if we draw a straight line towards the semicircle, towards the green semicircle, it will cut the semicircle, the green semicircle is points C and A. So for the same common extent point B, we also have here chord CA. Therefore, we can implement here rule 10. According to rule 10, rule 10 is true in any circle. If AB is a chord, we have here AB is a chord of this circle, and we have from the common extent point P, we have also tangent PT. So in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. We can definitely implement rule 10 in our drawing. Why? Because if you focus on this common extent point B, from this common extent point B, we have tangent BP to this green semicircle. Tangent BP is tangent to this green semicircle is point P. In addition, from the same common extent point B, we have also here chord CA. If we draw a straight line towards this green semicircle, it will cut this green semicircle at points P and A. So here, from common extent point B, we have tangent BP, and we also have here chord CA. So all the requirements of rule 10 are satisfied, and therefore according to rule 10, the following equation will be true, that BP square equals to BC times VA. Again, BP square equals to BC times VA. Repeat again. according to rule 10. According to rule 10, BP square, if you focus on the common standpoint point B, BP square equals to BC times BA. So this equation is the implementation of rule 10 in our drawing. Again, BP square equals to BC times BA. BP is the missing side, so we leave it as it is. So BP square equals to BC. BC is 1 times BA. BA in total equals to 5 plus 1, that is 6. So BA is 6. Again, BC is 1, BA is 6, and therefore in total BP square equals to 1 times 6, that is 6. So BP square equals to 6. We took out of this equation and finally found out that the missing tangent BP equals to the square root of 6 units in its length. Here BP equals to the square root of 6 units in its length. In the next step I copied this right triangle APB in a new page and we implemented the Pythagoras theorem on this right triangle APB. AP is the only missing side, AB is 6, the opposite AB is 6, and BP is square root of 6. So this is the right triangle APB that according to the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse of this right triangle is AB, therefore the square of the hypotenuse is AB square. And AB square must be equal to AP square plus PB square. Again, AB square equals to AP square plus PB square. AB is 6, therefore AB square is 6 squared, that is 36. And it is equal to AP square. AP is the missing side, so we leave it as it is, plus PB square. PB is square root of 6, therefore PB square is square root of 6 squared, that is 6. So in total, we should find out that 36 equals to AP square plus 6. We subtracted 6 from this equation and finally found out that AP square equals to 36 minus 6 is 30. We took out of this equation and finally found out that the missing side AP equals to the square root of 30 units in its length. So this is the missing side AP. This is equals to the square root of 30 units in its length. AP is the diameter of this green semicircle, and therefore the radius must be equal to half of it. So the radius R is AP over 2. See it again. The radius R of this green semicircle equals to the diameter AP over 2. AP is square root of 30, therefore AP over 2 is square root of 30 over 2, that is the radius R of this green semicircle. And our mission is to find out the area of this green semicircle. The area of this green semicircle equals to pi r square over 2. The area of the green semicircle equals to pi r square over 2. So it is pi r is equal to 30 over 2, therefore r square is equal to 30 over 2 square divided by 2. So the area of the green semicircle in total equals to pi. Square root of 30 square is 30, over 2 square is 4, divided by 2. So in total, the area of the green semicircle equals to pi times 30 over 4 over 2. 30 over 4 over 2 is 30 over 4 times 2. So in total, the value of this expression is 30 pi over 4 times 2. 30 over 2 is 15. So in total, the value of this expression is 30 pi over 4. 30 over 4 is 3.75. Therefore, in total, the value of this expression is 3.75 pi, and 3.75 pi is 11.78. So in total, in both methods, we actually found out that the area of this green semicircle equals to either 3.75 pi square units, or in terms of numbers, it is equal to 11.78 square units. Okay, thank you very much.